Hello and welcome to chapter 13. I would strongly say sit back and relax because this is probably going to be the longest lecture that we have, as this is the longest slides we've ever had, sitting out almost double the length at 43 slides. Wow! But this one actually deals with a lot of information. Fortunately, 13 probably hasn't been a lucky number for some. Some it may actually be a truly lucky number. But we're going to do a lot of correlation and linear regression here. So we're going to really study the relationship between two intervals or ratio level variables and develop numerical measures to express the relationship between the two variables. It's a lot of Excel that comes into here, but we're going to try to work through these and get y'all the best knowledge. So, of course, you know how it goes. Learning objectives. What are you going to learn in this chapter? First off, you're going to explain the purpose of correlation analysis. We're going to calculate a correlation coefficient to test and interpret the relationship between two variables. Apply regression analysis to estimate the linear relationship between two variables. Evaluate the significance of the slope of the regression equation. And evaluate a regression equation ability to predict using the standard error of the estimate and the coefficient of determination. Yes, we are determined to get this done. Calculate and interpret confidence and predicting intervals. And then finally, we're going to use a log function. Yes, log is here to transfer a nonlinear relationship. Sounds like a lot, but we'll get through it. Okay, guys? So what is correlation analysis? Well, basically, it's a group of techniques to measure the relationship between two variables. Mostly, we're trying to find a way to show, are they closely related to, independent variable, to independence, anyone. But we mostly stay with a lot of independent and dependent variables because we typically graph this. So graphing technique is going to be used a lot. They give a couple of examples. Does the amount of health tech spend per month on training its sales force affect its monthly sales? Does the number of hours students study for an exam influence the exam score? And both of those would probably be highly correlated to each other. Honestly, people would probably assume if you study more for an exam, yeah, your exam score will go high. But in some cases, that could have the opposite effect. Anyway, that's a good research item to look into. So they're going to use this example throughout this whole chapter about sales representation, sales calls, and copiers sold. And the first way that they're going to look at this is a scatter diagram. Now, a scatter diagram in itself is just taking the 2 points, sales calls and copiers sold, making sure which one is the independent variable, and that is going to be scaled on the x-axis. It is the variable used as the predictor, while the dependent variable is going to be on the y-axis. So, if you don't remember which one that is, x is the horizontal, y is the vertical on a graph. So, when we look at sales calls and copiers sold, if I want to know which one is the dependent variable, again, it has to rely on another variable. We're really going to see very quickly copiers sold is the dependent variable because it's dependent on how many calls are made, while a sales call is more independent. It's based on the person. So unfortunately, I can't sell many copiers if I don't make many calls. It's usually how it goes. So what we're going to do with a scatter diagram is we're going to basically graph it. So that's how we're going to do. What we're going to look at it is this, is that we're going to see if there's any kind of pattern, kind of like a line going through. And as you can already see, these dots are kind of grouped pretty close together also. So that could mean that there's a high correlation between sales calls and copiers sold. In fact, the more sales calls that it looks like, the more that we typically would sell. Okay, that's just observations that are going on in the scatter diagram. So next, we have the correlation coefficient. And this is that measure of that strength of the linear relationship between two variables. Now, when we talk about linear, we're talking about a line, okay? That's all it really is finding this line through our dots. Basically, a little slope item that we have. So the characteristics of correlation coefficient are: 1, the sample correlation coefficient is identified by the lowercase letter r. It's a pirate. R. It's a deal pirate. Anyway, it shows the direction and strength of the linear relationship between two intervals of a ratio scale variable. It ranges from -1 up to and including +1. Okay. A value near 0 indicates that there's a little linear relationship between the variables, and a value near 1 indicates a direct or positive linearship. Well, of course, a value of -1 indicates an inverse or a negative linear relationship between the variables. How does this look? Well, this is how it looks. Woo! So, these two graphs right here, one actually shows what our correlation would be. If it's -1, we have a very strong negative correlation, basically perfect. If it's -1, closest to 1, strong. -0.5, we have a moderate. If it's getting closer to 0, it's a weak negative, if it's still negative. If it's 0, there's no correlation. And then, of course, on the other side, the closer we get to 1, the stronger our relationship is in the positive light. So, bottom graph right down here shows a no correlation. This is actually, sorry about that, between income and number of children. Look, there's nothing, it's everywhere. Weak negative correlation between price and quantity. Notice again that you can see they're kind of grouped up, a little spread, but you can slowly see a line or a pattern form where it's going downward. And here's a strong positive correlation. In between hours studied and score. See, they're good bunched up, and more hours. And it seems like we see an upward line actually being formed. Nice. So how is correlation coefficient determined? Again, they're going to use the example of the sales calls. Here's a bigger picture of all the sales calls and copiers sold. And again, they're going to coordinate it off. Now, drawing lines through the center of the data actually establishes quadrants. These two variables are positively related when the number of copiers sold is above the mean and the number of sales calls is also above the mean. The points appear in quadrant 1. When the number of sales calls is less than the mean, so is the number of copiers sold. Those points appear in quadrant 3. So that's what they really did, is that they separated this all, and they found the mean of our data. Y'all remember mean. It's not mean. It's not mad at you. It's not bullying you. It just wants to find the middle. It's finding the middle ground. Yay! Whatever that mean number is. And that's where they draw their line. And again, this really does show us more of a positive scale by showing more of the further ones up here in quadrant 1. But it does show that there is a correlation. If you do less sales calls, you sell less copiers. So now we get a fancy formula. Again, apologies. Still have the cough from COVID. Try and knock it out. So, how is the correlation coefficient determined? Well, now we get to find the deviations from the mean number of sales calls and the mean number of copiers sold. Then multiply them. The sum of their products is 6,672. Okay? And it will be used in formula 13-1 to... Oh, yeah, they always do formula 13-1 instead of what they really are to find R. We also need the standard deviations. The result, R equals 0.865, indicates a strong positive relationship. Yay! So, this is our fancy formula. We know and love the fancy formula. So sum of x minus x bar times y minus y bar. So remember, you have to do the multiplication first. And then sorry. Sum it and divide by n minus 1 because it is a sample size. And standard deviations of x and standard deviation of y. So they have it all right down here to show you how it works, how it looks, and we come out to that 0.865. Notice that it is close, really close to 1. So we do show a strong positive. So again, they have this. Another example, the Applewood Auto Group marketing department believes younger buyers purchase vehicles on which lower profits are earned, and older buyers purchase vehicles on which higher profits are earned. So right there, that sentence alone tells me a lot about this Applewood. Is that they kind of cheat a little bit on the customers, or their customers are very knowledgeable when they're younger, and the older is just, I won't pay sticker price. Anyway, sorry. They would like to use this information as part of an upcoming advertising campaign to try to attract older buyers because, of course, we want more profit. We're business. Profit is everything. Develop a scatter diagram and then determine the correlation coefficient, which this be a useful advertising feature. Alright, first off, they do not give us the data. The data is actually in the book. We're not going there because we're just showing the PowerPoint, and they really should put data in the PowerPoint, but they sum it. The scatter plot of it, as you can see, it's almost everywhere. This does not really look like there's a lot into the line. Now, they're going to suggest that there is a positive relation does exist between age and profit. But it definitely does not look like it's a strong relationship. We can probably barely make out a line going positive. Well, next they calculate R, which happens to be 0.262. So it does show that the relationship is positive, but weak. Oh no. The data does not support a business decision to create an advertising campaign to attract older buyers. It's just not a strong enough relationship. Next, testing the significance of R. What? Y'all think we're going to test this stuff? Of course we're going to test it. We test everything in the last few chapters. So we call that the sales manager from North America Copier Sales found an R of 0.865. Could the results be due to sampling error? Remember, only 15 salespeople were sampled. We asked the question, could there be a zero correlation in the population from which the sample was selected? We're going to let lowercase p represent a correlation in the population and conduct a hypothesis test to find out. Yes! Now, I call it lowercase p, but it's actually rho. That's the actual Greek term. So, rho is next. So we're going to find out what I have to make sure I keep using the Greek letters. Rho is going to equal to 0, or rho is going to not equal to 0. This will mean that the correlation of the population is either 0 or different from 0. Our most likely guide is probably going to be rejecting the null. We hope that we do. But we're going to select the level of significance. We're going to use 0.05. And we get to bring back our good, useful t-test statistic. Yay, t's back. Woo woo. And remember, since we have a two-tail test, because pretty much all rows testing for the correlation is going to be two-tail, we use Appendix B.5 in your book. Those good old t-charts. For degrees of freedom, it's going to be n-2. Okay? So since we have 15 people, we're on -2, and our degrees of freedom is 13 at that level of significance. Alright. So, we also see in our bell curve, once we figure out what our t statistic is, which is 2.160, we have made our decision rule. We can only reject the null if it falls either below or less than negative 2.160 right here, or positive 2.160. So it's got to either be greater than or less than. It's got to fall in the shaded areas. If it lands in between, we do not reject. Fun part about two tails. I know y'all just enjoy it so much. So here's our t-test for correlation coefficient. Yes, another formula. Never going to stop with the formulas, guys. Y'all know y'all love them. So since it's correlation coefficient, guess what? Lowercase r is back with 0.865. And we take the square root of our data set, the total numbers of our sample set, -2. So, kind of looks like degrees of freedom right there. And then divide by the square root of 1 minus our lowercase r, so our correlation coefficient, squared. Yes, you definitely know I'm probably going to throw that in Excel. So, we're going to be doing these formulas again, like I've been showing y'all in Excel, and probably pieced out, so it makes it a little bit easier to follow along what's happening. It's always good to piece them out. So, we find out that the t actually equals, for our t-test, 6.216. So, since it is greater than 2.160, falls in the shaded, so we must reject the null. So when we interpret this, we find out that there is a correlation with respect to the numbers of sales calls made and the number of copiers sold in the population of salespeople. Yes, it just proved our theory that our correlation coefficient is correct. Now, we can have one tail test. It's like, oh no, one tail. Yes, one tail is back. Remember, as always, if it's equal or not equal, 'tis two tail. So 0.05 actually gets divided by 2 in the level of significance because it actually is 0.025 when we look at the tail. But when it's one tail, it really is 0.05 because we're only looking at one part of the bell curve. So, always fun. Watch out what it asks you for. So, for this one, they're using that Applewood auto group example. Remember where the buyers are not really having a strong correlation, but there is one positive one, slightly. So, we're going to test our conclusion by conducting a hypothesis test. That correlation is greater than 0. Okay, so that means, again, the alternative is the question we're asking. Is it greater than 0? So rho for our alternative will be rho greater than 0. Okay, so that means, again, for our null, rho has to be less than 0 or equal. Okay, always has the equal sign in our null. Okay, next, we're going to use that 0.05 of significance. We're going to select the test statistic. Again, we're going to use T. Okay. So, according to this test, the degrees of freedom in this test was, again, n minus 2. We're going to use 180. Minus 2 could come out to 178. But Appendix B doesn't have 178. So they're going to use 180. That's what they're going to tell you to do in the book. And critical value is 1.653. Okay. It's probably a limitation on the table. But that's fine. Now we're going to use the formula that we did just a while ago. So, with this, we're going to formulate the decision rule. Again, T, since we're dealing with greater than, we will reject the null if T is greater than 1.653. And according to the calculations in itself, again, lowercase r was 0.262. We square root 180 minus 2, and then divide it by square root 1 minus 0.262 squared. So always multiply the top and divide. Comes out to 3.622. So we know that is definitely greater than our 1.653. So we're going to reject the null. So all this tells us is that there is a correlation with respect to the profits and age of a buyer. And it is pretty much showing that it may be a positive one. It's greater than 0. But there is a correlation. Nice. Now here comes the big bad boy in this chapter. And that is going to be regression analysis. Typically, if you have a graphing calculator, this will be a lot easier. Honestly, it will be. But that will be something that you have to look into. So, in regression analysis, we basically go ahead and estimate one variable based on another variable. Typically, the estimate is the dependent variable. And the variable used to make the estimate or prediction is going to be the independent variable. So in our case of the sales calls and copiers, we're going to try and estimate the copier sales based on sales calls. The relationship between the variables is always linear. This is why it's called a linear regression. Both the independent and the dependent variables must be interval or ratio scaled. So be cautious of that. Again, an equation that expresses the linear relationship between two variables. We're actually going to be using a simple principle called the least squares principle. Okay, that's typically the most common one to use in calculating regression on our own. All right, so least squared. So when we look at regression analysis, our objective is to use the data to position a line that best represents the relationship between the two variables. So we're really trying to find the best line. Now, the first approach is to use a scatter diagram to visually position the line. But there could be actually multiple lines that can actually be used. So it depends on judgment. We would prefer a method that results in a single best line. That's really all we're looking for, is the best so we can properly predict what would happen. That's what we're trying to do, is try and get that estimate going. So this is why we use the least squares principle. So it's going to be a mathematical procedure that uses the data to position a line with the objective of minimizing the sum of the squares of the vertical distance between the actual y values and the predicted values of y. Sounds like a lot right there, but really all it is, again, is using mathematical equations to, again, find the best line that works for the points and data that we have. And they do provide 3 little areas. So they have the least squares line right here. And you can see that they're really trying to show how far apart the actual point is from the line. Then they have the line drawn with a straight edge. It's a little bit bigger right here at this point, at 6. So this was at a straight edge, going where the first point is. And then this is a different line drawn with a straight edge. That's all they're saying. And we can actually see bigger groups. Again, what we're trying to do is find the best line. Strange examples, but we'll go with it. Alright. So how are we going to do this? Well, here's the basic equation. So, we're going to be using the general form of linear regression equation, which is y with the little hat equals a plus bx. Okay, if you remember this from your math courses, this is, of course, the basic slope equation. Really all it is. So, y hat is the estimate value of the y variable for a selective x value. A is the y-intercept. B is the slope of the line. Okay. And then x is any value of the independent variable selected. Most of the time, we probably saw this as a plus mb or mx. Somewhere around that. Trying to remember my old school math at the same time being buzzed by everybody. Okay, so the formulas for A and B are with our slope of the regression line, B is going to equal to our little r, with the standard deviation of y divided by the standard deviation of x. Now, our y-intercept is going to be A is going to equal y bar minus b multiplied by x bar. Nice. A lot of fun stuff that goes on right here. So again, they're going to use the copier cells, and the sales manager gathered the information on the number of sales calls made and the number of copiers sold. Use the least square method to determine a linear equation to express the relationship between the two variables. What is the expected number of copiers sold by a representative who made 100 calls? So the first step is to find the slope of the least square regression line, B. Now we've already found little r, our coefficient, correlation coefficient, at 0.865, and we're going to multiply by the standard deviation of y divided by the standard deviation of x. So 12.89 divided by 42.76 equals to a grand total of 0.2608. Next, we find A. A is going to equal to y bar minus b times x bar, which equals to 45 minus 0.2608 times 96, which equals to 19.9632. Nice. So there's our y-intercept and our slope. So our regression line for an estimate is y hat equals to 19.9632 plus 0.2608 times x. So whatever our number is, we can now determine y. So if a salesperson makes 100 calls, we'll go ahead and insert that as x, since that was our x is our calls. And we can actually determine that if they make 100, we can properly estimate that they're probably going to sell 46 copiers. And we can keep doing that for any number that we need to. So here is where they actually are drawing the line. So drawing the line. I believe you drawing the line for regression. Drawing the line. Oh yeah. Draw the line for regression. Alright. So the least square equation can be drawn on a scalar diagram. For example, the fifth sales representative is Jeff Hall. Don't know why they picked the fifth one, but we like Jeff Hall. Jeff Hall. Jeff Fafa. He made 164 calls. His estimate number of copiers sold is 62.7344. The plot x equals 164 and y hat equals 62.7344 is located by moving to 164 on the x-axis and then going vertically to 63.7344. I think they have a typo. We found a typo. It's supposed to be 62.7344. Oh, that happens. Anyway, the other points on the regression equation can be determined by substituting a particular value of x into the regression equation and calculating y hat. Basically, the estimated sales has the proper line of regression for us, the linear regression. And we can basically plot out that whole line. Again, if you have a graphing calculator, it actually works very well by inserting certain points. That's if you really want to see what's going on. Right here, since we're all about math, the lovely, lovely math, we're actually diving deeper into how this all happens. But at the same time, we're using Excel. It's like everybody's like going, yes. Can't wait till you start using Excel. Oh well. So we're about halfway through the slides already. Let's see if it takes a lot longer. Let's go. So we're going to do a test. Why not? Because this is statistics. We must test everything. Make sure that we're good. So the regression equation slope test. It's basically going to be testing slope. Yes, for significance. We're going to test the hypothesis that the slope of the line in the population is 0, which means no correlation, no relationship. So, if we do not reject the null, we conclude that there's no relationship. They're not independent or dependent. What we want is to reject that. So, when testing the null hypothesis about the slope, test statistic is within minus 2 degrees of freedom. There's our n minus 2. We begin with the hypothesis statements of beta equals 0, or beta does not equal 0. So, our 6 steps. We're again going to recall the copier cells and identify slope as B, and it's our estimate of the slope of the population beta. We conducted a hypothesis test. State the null and alternative hypothesis. Well, we want beta to be greater than 0. So, our alternative is beta is greater than 0. While null is beta is less than or equal to 0. We're going to do the level of significance. We're going to use 0.05. Notice, again, this is going to be a one-tail test because we're using greater than and less than. Select the test statistic T. Hi, T. It is back for us. And we're going to formulate the decision rule. We're going to reject the null if somehow T, when we test our statistic, is greater than 1.771. We're going to make a decision. We're going to reject the null because T is actually going to equal to 6.205. Now, how does it equal to 6.205? Well, we take the slope, so B minus 0, okay, and divide by the standard deviation of B. So, that's going to basically be a null. So 0.042. Within minus 2 degrees of freedom. Yes. So again, it comes out to 6.205. Again, we're going to go through all this with our practice problems to show how things are working. Alright, next we interpreted that the number of cells calls is useful in estimating copier cells. That's all we care about. Does it actually work for us? Then we can use Excel. Excel has a lot of fun stuff. So this is actually showing the regression equation for our Excel. Nice. All right. So evaluating a regression equation's ability to predict. Perfect prediction is practically impossible. It's almost all disciplines, including economics and business. Fortunately, we cannot always be perfect. We're practically perfect in every way. Yes. The North American copier sales example shows a significant relationship between sales calls and copier sales, with the equation as 19.9632 plus 0.2608 times the number of sales calls equals our number of copiers sold. What if the number of sales calls is 84 and we calculate the number of copiers sold is 41.8704? We did have 2 employees with 84 sales calls and they end up just selling 30 and 24. So is the regression equation a good predictor? That's always going to be the question. Is it a good? It's an estimate. So it's not going to be totally perfect. It's going to be a little bit inaccurate. So we need to find our error where we can be suitable. So this is the variation, the standard error of estimate. So this is going to be the measure of dispersion or scatter of the observed values around the line of regression for a given value of x. It is the same units as the dependent variable. It is based on squared deviations from the regression line. Small values indicate that the point clustered closely about the regression line is computed using the following formula. So the sum of y minus y hat squared divided by n minus 2 square root. So this is going to be the same concept that we have seen in the standard deviation all the way back in chapter 3. So it's going to bring a lot of memories back. We hope. So we calculate the standard error of estimate in this example. We need the sum of the squared differences between each observed value of y and the predicted value of y, which is why we use a spreadsheet to help with the calculations. Yeah, them showing off Excel again. So again, piece by piece, just to really help things work out. So the standard error of estimate is 6.720. Okay. If the standard error of estimate is small, this indicates that the data are relatively close to the regression line and the regression equation can be used. If it is large, the data is widely scattered around the regression line and the regression equation will not provide a precise estimate of y. So tell me why I can't estimate this. Tell me why it's just another trick. Anyway. So, next, the coefficient of determination. Yes, this is the proportional of the total variation in the dependent variable y that is explained or accounted for by the variation in the independent variable x. Yes. So basically it's another way to determine variation. How far away or how many different variables. So it ranges from 0 to 1. It is the square of the correlation coefficient. So basically r squared. It is found from the following formula. R squared equals SSR divided by SS total equals 1 minus SSE divided by SS total. So there's 2 ways we can actually equal this out. So in the North American copier sales example, the correlation coefficient was 0.865. Just square that when we get 0.748, this is the coefficient of determination. So if we know R, we're good to go. This also will help if we don't know R. Because again, if we know SSR and the SS total, or 1 minus SSE and SS total, we can actually go backwards. So both of these are from our ANOVAs from chapter 12. But this basically means that 74.8% of the variation in the number of copiers sold is explained by the variation in sales calls. So, pretty high percentage can be explained right there just by sales calls. Again, very strong. So, relationship among these. So, the standard error of estimate measures how close the actual values are to the regression line. When it is small, the two variables are closely related. The correlation coefficient measures the strength of the linear association between the two variables. When points on the scatter diagram are close to the line, the correlation coefficient tends to be large. Therefore, the correlation coefficient and the standard error of estimate are inversely related. So, basically, the smaller that our standard error of estimate gets, the larger we're going to see the correlation coefficient measure to show how much of a strength that the two variables have. So that's why they call it inversely. Basically run the opposite but mean the same thing. So, interference about linear regression. We can predict the number of copiers sold, y, for a selected value of number of sales calls made, x. But first, let's review the regression assumption of each of the distributions in the graph below. So, again, each of these distributions follows the normal distribution, has a mean on the regression line, and has the same standard of estimate, error of estimate, and is independent from the others. So, really, all this is doing is showing that the mean does fall on the regression line, but it can scatter a little bit. So, a little bit farther away. All it shows is that there's a number of possibilities and still be within the parameters of our estimate or regression line. So constructing confidence in predicting intervals. Using a confidence interval when the regression equation is used to predict the mean value of y for a given value of x. Okay, so all again, when we have predicting, we're estimating. For instance, we would use a confidence interval to estimate the mean salary of all executives in the retail industry based on their years of experience. Okay, love their examples. So confidence interval for the mean of y given x is y hat minus t times our standard error. So our s, and then square root 1 divided by n plus x minus x bar squared divided by the sum of x minus x bar squared. That sounds like loads of fun already to add on to more formulas from this chapter. Okay. So we'll use the prediction interval when the regression equation is used to predict an individual y for a given value of x. Okay. For instance, we would estimate the salary of particular retail executives who have 20 years of experience. And the only difference that we have between the predicted interval formula and the confidence interval is that we add an extra 1 within our square root. Nice. But these two different predictions can be made for a selected value of independent variables. In a confidence interval, the width of the interval is affected by the level of confidence, the size of the standard error of estimate, and the size of the sample, as well as the value of the independent variable. The prediction interval is also based on the level of confidence, the size of the standard error of the estimate, and the size of the sample, and the value of the independent variable. And the difference between the formulas is the one under the radical, or basically under square root. The prediction interval will be wider than the confidence interval. Okay, covering all our bases. So of course we gotta have an example. Why not? And it looks like it's been through the ringer. But again, we're going to use that copy your cells example. Determine a 95% confidence interval for all sales representatives who make 50 calls. And determine a prediction interval for Shelley Baker, a West Coast sales representative, because we want to add West Coast, who made 50 sales calls. Okay. So the first thing that we do is, again, we take our y hat, or basically our slope formula, and we're going to insert 50. We find out that our estimate on the regression line will be 33.0032. Okay. Confidence interval is going to take that 33.0032, and we're going to plus or minus, again, our t value, again, at 95% confidence interval. We find that it is 2.160. Again, use n minus 2 for degrees of freedom. Freedom! Multiply by 6.720. Okay, that is our standard error that we've already calculated. And square root 1 divided by 15 plus 50, which is our x, minus 96. That's the mean number of sales calls, squared, divided by that sum of x minus x squared, which was 25,600. Calculate all that fun stuff, and we get 33.0032 plus minus 5.6090, which again will give us a range, confidence interval, of 27.3942 up to 38.6122. Now again, the prediction interval adds an extra 1. So this actually increased to 15.5612 that we add or minus. So our prediction interval at 95% significance, our confidence interval, basically 95%, is 17.442 up to 48.5644. So again, the prediction takes a little bit, it's going to be wider range, just so that it can cover a little bit more numbers. But our confidence, that we're totally confident in that she should sell in, is a little bit smaller. So transforming data. Regression analysis and the correlation coefficient requires data to be linear. Again, it has to be a line. But what if the data is not linear? Okay, so we'll have to mold it to the linear form. So if data is not linear, we can rescale one or both of the variables so that the new relationship is linear. Common transformation includes computing the log to the base 10 of y, so log y, taking the square root, taking the reciprocal, squaring one or both variables. Caution: when you are interpreting a correlation coefficient or regression equation, it could be nonlinear, but we need to fix it. So for example, we have Groceryland Supermarket is a regional grocery chain. Located in the Midwestern United States, the director of marketing wishes to study the effect of price on weekly sales of their 2-liter private brand Diet Colas. The objective of the study is, to determine whether there is a relationship between selling price and weekly sales. Is there a relationship direct or indirect? Is it strong or weak? To determine the effect of the price increase or decrease on sales, can we effectively forecast sales based on the price? To begin, the company decides to price the 2-liter Diet Cola from 0.5 or 50 cents to $2. To collect the data, a random sample of 20 stores is taken, and then each store is randomly assigned a selling price. Now, we're going to figure out if there's a strong relationship or not. So the first thing that we end up doing is the scatter plot. Okay? So while doing the scatter plot, we find that there's actually a strong inverse relationship. So again, the higher the price goes, the less sales we make. Seems about right, huh? Less people are willing to buy when the price is high. Okay? We actually find out that this is an 88.9%. Wow. Now, the program that we're using is Minitab. We don't have access to that, unfortunately. That's why it looks all nice and professional right there. It's nice and pretty. So, the director of marketing decides to transform the dependent variable, sales, by taking the logarithmic to the base 10 of each sales value. Note that the new variable, log sales, in the following analysis is used as a dependent variable with price as the independent variable. Okay? So, by transforming the dependent variable sales, we increase the coefficient of determination from 0.889 to 0.989. So now price explains almost all of the variation in log sales. Again, they basically try to go, okay, yeah, we can fit the data better. So that's what really they did. They transferred the data to fit the linear relationship better. The regression equation is y hat equals 2.685 minus 0.8738x. Okay. So, y hat equals, again, that formula equals, if we put $1.25, we would have a 1.593 cells. Now, undo the transformation by taking the anti-log of 1.593, which would be 39,174, 39 bottles. That is if the price of cola is 1.25. They sell 39 bottles at $2. They sell 9. All they did was basically take the anti-log, go back to the original data that was taking. But notice that they did it on transformation. So, really what we're seeing is clearly as price increases, sales decrease. The relationship will be very helpful to grocery land when making pricing decisions. You'll see this a lot with store brands. They're going to do a lot of research and statistics to see what is the ideal price. What are they willing to put it as to the products that you're going to sell? This is also why you see a lot of times in Walmart, name brands are always going to be more expensive and their store brand is a lot less because they want you to gear to buy their store brand. Okay, so the time has come, the walrus has said, to finally hit practice problems. Yes, you stayed with me this long, might as well stay along a little bit longer as we work through these practice problems and probably setting up the Excel for the homework. Let's see what we do. Alright, so question 3. I think we actually have 5. We actually have quite a bit. So, not bad bunch of questions. So, Buy Low Appliance Superstore has outlets in several large metropolitan areas in New England. Yay, New England! Woo! The general sales manager aired a commercial for a digital camera on selected local TV stations prior to a sale starting on Saturday and ending Sunday. She obtained the information for Saturday and Sunday digital camera sales at the various outlets and paired it. When the number of times the advertisement was shown on the local TV stations, the purpose is to find whether there is any relationship between the number of times the advertisement was aired and the digital camera sales. The pairings are Providence 4:15, Springfield 2:8, New Haven 5:21, Boston 6:24, and Hartford 3:17. Okay, let's go ahead and get Excel. Oh, that's an old one. New blank. Okay, so we have 4 and 15, 2 and 8, 5 and 21, 6 and 24, 3 and 17. Okay, we'll make this big. Hola, data. Okay, so this is airings, and this is thousands. Alright, so this is how much sales that they did in thousands and airings. Okay, so let's see, data. Insert, there you are. So scatter, there we go. So again, you can put in your scatter plot. Usually the independent will always be the first column. That's why it's on X. And the dependent is going to be the second column. So again, sales is the dependent variable, because it is related to how many airings that we have. So if you want to go ahead and figure this out, we can actually grow it. This looks like a positive relationship. So next, we want to figure out correlation coefficient. So of course, let's see. Well, we were hoping that we'll have it. Well, it all works. Anyway, so we can calculate this all on Excel. Let's actually going to try and go for it a little bit easier. But the first thing that we have to do is find our means. Okay. So we know mean is auto sum. And we take that and divide by how many numbers. We have 1, 2, 3, 4, 5. Same thing. Oh, you can actually drag across. And there we go. Okay. Now, we found our mean. Yay, our mean. So, going back to correlation all the way through all these slides. So we can have the formula. So we can actually piece it all together. There's our correlation coefficient. So, back to Excel. Okay. So first thing that we had to do was actually create the mean. So we have the first top is going to be the sum of x minus x bar times y minus y bar. So we'll have x minus x bar, y minus y bar. It's going to equal to 4 minus our average. There we go. And y is going to equal to our thousands minus 17. And remember, it's the multiplication of the two. So x minus x bar. So enter. So that's going to be equal to this times this. Okay. And we need the sum of this. Auto sum. So there's the top part. There's 36. Next we got to do the bottom. So we're going to go ahead and eliminate the chart. We did the chart. That's fine. Equal. Okay, so using our formulas, functions, we're going to find our standard deviations. Remember, we're going to actually multiply it by both x and y, so we need two of these standard deviation formulas. Standard deviation S. And just highlight the range and hit OK. Now, this means we have to go back to the formula a couple of times, just because we're hitting OK to get through the box. But also remember that we're going to multiply it by n minus 1. So again, this is how many? So we have 5. So 5 minus 1. So that will be our bottom to find the correlation coefficient. So let's go back to our problem. All right, so back to Excel. So we have 36. And this is going our correlation coefficient. So we're going to put it out here. Correlation coefficient, or R. Oh, I like how I did that. R is going to equal to this number, R. Basically sum of x minus bar times x y minus bar divided by our bottom, which was the 2 standard deviations. Again, use the formulas. Helps it a lot quicker because I know time is of issue. Times 5 minus 1. And we come out that our correlation coefficient is 0.92952. Which, even with our chart, again, if I insert chart, highlight data, so if we have the chart right there, and you can label it if you want to, we saw that there was a positive. We know that the correlation coefficient, 0.92952, shows a very strong positive associate between the variables. It's close to 1. So we do know that we can determine that, yes, the number of airings does correlate to the number of cells. It's very positive in its rights. Okay. So that's one. We'll actually go and change this. I'm going to rename it as, since this was question 3 in the practice problems. Next, we're going to go to question number 11. Whoop. See if we actually need to use Excel for this one. Alright, so the Airline Passenger Association studied the relationship between the number of passengers on a particular flight and the cost of the flight. It seems logical that more passengers on the flight will result in more weight and more luggage, okay, which in turn will result in higher fuel costs. For a sample of 15 flights, the correlation between the number of passengers and the total fuel cost was 0.667. Okay, so they already did the correlation for us. Is it reasonable to conclude that the number, as there is a positive association in the population between the two variables, use the 0.01 significant value? Alright. Alright, so the first thing that we have to determine is our null hypothesis and our alternative hypothesis. Now, since they're looking at a positive association in the population between the two variables, this does tell me that they want to look at greater than 0. So rho, that lowercase p, for null has to be less than or equal to 0. Well, our alternative is going to be rho is going to be greater than 0, because we want to show that there is a positive association. We want to reject the null. Next is figuring out t value. Okay. So remember, when we look at this, our degrees of freedom is n minus 2, which n happens to be 15 flights. So 15 flights minus 2 equals 13. So we need to pop up our nice table. Here's our table. And goodbye. And we'll look at the level of significance for a one-tailed test, because we're using greater than and less than. Remember, if it's equal, it's going to be two-tailed. So we're going to find 13. And according to 0.01, on one-tailed test at 13, our t, or critical value, is 2.650. Okay, so this means we're going to reject the null if t, when we calculate, is greater than 2.650. Okay. So next, we're going to use the formula, which means going all the way through the slides. And I know y'all already written down the formula, because y'all guys are awesome. And we're going to be using this formula, test for correlation coefficient. Okay. So back to the problem, because we need the numbers. Since this doesn't look like we're going to be using the Excel much, since it's just really going through the formula. So, but I'm probably going to just put it in the Excel, because our calculator is not the greatest that we have on doing all these square roots. So, might as well have Excel calculate for us. So this is going to equal, I don't know if it's going to let me blow it up too much to show. So this is going to equal to 0.667, and we're going to take the square root. Square root, and the number is going to be 15 minus 2. Okay, now make sure that it does state multiply, okay, or it's going to naturally try to add. Always be careful of that. And I'm going to always put the numerator and sorry, the denominator separate on Excel, so we can actually see them now, so we're not like making a very complicated formula, especially if you're trying to recreate this based on my stuff. So the denominator is going to equal to the square root of 1 minus power, so another formula, of our correlation coefficient, 0.667, comma, squared. And make sure you close out the parentheses. Hit enter. So there's our numerator and there's our denominator. And hit equal. And we're going to just divide the two. Simple as that. So 3.227807. Now, if you really want to compute this in Excel, just want to have the formula put in, you can do that. I'm going to actually show you how to do it. Okay, so we're just going to input the numbers that we know we pulled from the problem. So this is going to be R, or correlation coefficient, 0.667. And then the sample size, so I'm just going to put size is 15. And then you can just do the formula. So equals, again, we're going to put in parentheses whatever R is, multiply by the square root of whatever our sample size is, minus 2, because it's always minus 2 for this formula, and then divide it by, again, put it all in parentheses, square root of 1 minus the power of our R coefficient, comma, 2. There you go. So, if you put the formula in like this, where wherever the problem is, you pinpoint R, sorry, so coefficient and the size, boom. Yes, forgot I needed extra parentheses. It will calculate out the same like I did here by just putting in the numbers. But here, now I have the formula put into Excel. So if I ever change numbers due to a different formula, like this is 0.989 and this ends up being 20, it will automatically calculate for us. Work smarter, not harder. So, formula does not change, but we do know that the t value was 2.650, which would mean, again, that we're going to reject the null because it's greater, our actual t statistic is greater than that 2.650, the critical value. So there is a positive correlation between the number of passengers and the plane rate. Okay. Next question. This one's going to bring a lot of fun. We got this though. Okay? So, Bloomberg Intelligence listed 50 companies to watch in 2018. 12 of the companies are listed here with their total assets and 12 months of sales. Okay. Let sales be the dependent variable and total assets be the independent variable. And they want us to draw the scatter diagram, compute the correlation coefficient, determine the regression equation, and for a company with $100 billion in assets, predict the 12 months of sales. Okay. Lots of fun there. So here we go. Excel, come to us. So this is actually called question 17. Okay. So it also does the correlation coefficient and wants to do the scatter plot. We can do that. We can just need to input the information. So again, we have 12. So we have assets and we have sales. So 134.47, 68.13, 16.15. Fun part of have to manually input. Takes a little bit. Again, I'm not worried about who I'm dealing with because that is unimportant information for me since we're only looking at the numbers. And last one. Alright, so we know how to calculate coefficient, correlation coefficient. We can even go, since we're all in the same slide, right back here. So we're going to have to figure out standard deviations. Yay. So again, we got this formula right here. In fact, if I want to be fun, I can actually go ahead and copy this formula. Go copy. So we're going to copy the formula. Come here, question 17. Paste. Okay, so basically it gives us the same formula right here. So same numbers, but since we're dealing with a larger data set, we have to extend our standard deviations. And this is no longer 5, it is now 12. So that is our denominator. Okay. That's fine. Again, blow it up a little bit. Okay. So, x minus x bar and y minus y bar. We don't have the means yet, so let's calculate the means. So again, we're going to auto sum and divide it by 12, since that's what we have. Drag it across, and it's a little bit bigger number. It's a funnier number than what we usually have. So again, we can take that number, and if we actually do minus like this, problem is that we're going to run into is if I drag, it's going to follow the same path. So there's two ways we can do this. We can basically copy this formula, paste it down all there, or do a simple do each one, tell it to use that one. And yes, it's going to show the green little arrow because we tell it to use A16. So quickly, 16. So it may seem takes a few more seconds to do it this way, but next, if you ever have a data set that you just want to use the same info, you can just now put the new numbers in. Okay. So notice what happens here. It's basically the same. So let's see if it does the same for each formula. Wow. So again, just drag across. Boom. So we don't have to do all that typing again. Just a quick drag across. And we have all of our numbers. Again, the longest it takes is to set up the data. And there we go. Again, you can double check if you want to, make sure they all did B16. That's fine. Next, we got to do that multiplication. So x, we're just going to say these two are going to be multiplied. So x minus x bar times y minus y bar. So equal, boom, times, boom, drag down, and find the sum. And remember, correlation coefficient is basically going to be those two divided by each other. So equals the sum divided by that. And we come out to 0.991567. So pretty good line there. So strong coefficient, again, if I decide to do a scatter plot, which again you can highlight and then go to insert and do our fancy scatter plot. It looks quite funky, but we can still show that there is a positive effect going on. It is going higher. Just a big lump sum is right here in the corner, but you can still see it as we go. Next, we need to do our regression equation. So, back to knowing our formulas, all the regression equations. There they are. So y hat equals a plus bx. So now we have to figure out these items. So first b. Alright, so the best thing that we can do with these formulas is about the same that we've been doing. So we know b equals r sy divided by sx, and then a is going to equal to y bar minus b times x bar. Okay, so let's do these. So go back to our problem. Question 17. Sorry, I know I need not to do that. All right. So XL. So we're going to find the slope and the y-intercept. Alright, so slope, again, I'm going to put it all together, is going to be our correlation coefficient. That takes the time to actually do. Multiply, and then in parentheses, again, our standard deviation. Make sure you put the point S. Alright, So again, when we do the standard deviation, make sure you're highlighting. We close the parentheses, and we're going to divide by the standard deviation of y. Yeah. So we have standard deviation. Always make sure you use the sample one. Alright. And then we'll highlight. Boom. And then close our main parentheses and hit enter. I think I switched them by accident. Okay, so I may have switched that, to be honest. I mean, memory's not good when you're going through all those slides, so let's make sure I put the right one on top, just for double checking. Nope, SY is supposed to be above SX. So I did switch them. Sorry, guys. That's why we got Excel, because we can easily fix that. Go here. We're going to tell it to use this one. So, easy way, just where there's A, hit B. So that's the B range. And this is going to be the A range. Quick switch. So make sure you do put the Y on first. So wherever your dependent is, so sales divided by assets, the standard deviations. Again, if I put the formula in, next time I come through, I can just change the data and already have the formula in. Or as you saw, like I did with question this one, where I just copied from a previous Excel and just changed the numbers that I need to. All will work. Now, the y-intercept. Okay. So we need to figure out the y-intercept, which is the y-mean. So, equal. We figured out the y-mean minus our slope. So we're going to put it in parentheses. Slope times our x. So again, all that information, all that information is already in for us. So we can just put in the formula, and we come out to 1.57337. Nice. Again, we may have rounding that could happen. That usually does happen, so keep an eye on that. Now, D on our problem actually asks for a company with 100 billion in assets. Okay, predict the 12-month sales. So when we want to do this, there's an easy way to do y hat. So y hat, that's basically going to be, again, our sales figure, our estimate. And the formula is our y-intercept minus our slope times. Now, it's times by x, so it's the number that we want. So, we can pick, we're going to pick another square. I'm going to just do this square. hit enter, and we're going to put this as just simple put x. I mean, it's the number that we're looking for. So x is 100 billion. Oh, it's not minus, it's plus. Why did I do minus? Ma, babe. I'm thinking minus like crazy. Formula's plus. Sorry, that's my bad. Okay, so y hat will equal to wherever we change x to. So if I want to find for 115, there it is. There's where y should be. So 100 should be 46. See, that's a good way when it's a negative. We know we did something wrong with the formula. Mistakes happen. So always double check your formulas. Make sure you got them correct according to the data. Okay, so that's question 17. All right, question 23. We're getting there, guys. So question 23, of course, as we know, these practice problems, they go basically along the lines of every little math subject that we've done. So this one's going to take exercise 17. So we're going back to that one. And they have a regression equation of y hat equals 1.85 plus 0.08x. Okay, so they basically rounded a little bit with the numbers that we have. That's fine. The sample size is 12 still, and the standard error of the slope is 0.03. Okay, use the 0.05 significant level. Can we conclude that the slope of the regression line is different from 0? All right. So this one focuses on testing the slope of regression, you know, with beta, or that funky B with the little extra tail line. So when we want to see if it's different from 0, we'll be looking at, does it equal 0 or does it not equal 0? And already knowing that, we know we have a two-tailed bell curve that we're dealing with. So it's a two-tail. So we got to watch out for that as well. And since we're still using t, we know we're going to have to use that. So again, our null is going to be beta equals 0. Or basically there is no difference. Where our alternative is beta does not equal 0. Because there is. Again, we're going to be using, went the wrong way. Coefficient determination. This right here. So we're using the test for slope as we figure this out. Okay, so first thing that we have to do, of course, is figure out the t value. So when calculating the t critical value, remember, we still do n minus 2. So we have 12 minus 2, which again equals 10. Now, on our table, since we have a level of significance for a two-tail, we're at 0.05. So 0.05 level of significance. And looking at 10, means we're going to be sitting at 2.228. Now, since it's two-tailed, remember, that's a positive 2.228 and negative 2.228. So it cannot be. So if we're going to reject the null, it has to be less than negative 2.228 or greater than 2.228. If it falls in between, then we do not reject. Next is now figuring out our testing statistic. So we're going to show something pretty cool. All right, so since we're still working on here, we're actually going to look at formulas. Should be right here. Alright, so there's a neat thing to actually help us with regression when it comes to Excel, and we need a button called Data Analysis. Now, if yours has it, then yay. If it doesn't, you need to go ahead and click on File, Options. We need to go to Add-ins. And you see down here that says Manage Excel Add-ins. We want to hit Go. Okay. And then we want to do this Analysis Tool Pack. So we want to check the box, hit OK. And there it is. It'll pop up. The reason why we want to do this again, this is going to provide us with actual regression, which is something that is actually pretty cool. So there we go. So we're actually, as you can see, this actually has mostly our statistics. With our t-test, two sample equal variance, non-equal. Wow. So here's regression. So click OK. We're going to input the Y range. Remember, this is our dependent. So this is going to be cells. Input the X range, which is our independent. Whoop. I didn't get away from that. Okay. Even lets us do confidence level, because constant is 0, labels, all this fun little stuff that we're probably going to be playing with. So, new worksheet, go OK. And look at this. This is what McGraw-Hill has for y'all. It actually gives us p-value. So, yeah, we finally got the statistics for that. It's all been updated now. So we don't need that p-value calculator again. But we have our t-stats for our intercept, x variable. Now it's time to actually look at this. The reason why we need this, especially for problem 23. I don't remember which problem we're on. Is that we need the standard error right here for the formula. Okay. So remember the formula. Whoop. Is b minus 0 divided by SB, which is the standard error when it comes to that B, which of course is right here. Cells calls X right there. So we want to take what our slope is in this problem, which is 0.03, well, 0.08, and basically divide it by standard area of the slope, which is 0.03, but I wanted to show y'all how to do the Excel, because this is the actual regression of our thing, which is cool. Shows the regression, SS. This is our ANOVA table right here, which we remember that from chapter 12. So a lot of fun stuff here. Standard error, R squared, multiple R. So definitely when we get into multiple regression. Okay. I just love it when we get a new play toy. So, but for us, since it already gives us their items, we can go ahead and calculate. Okay, I was getting a little bit too excited that we have that. So 0.08 divided by 0.03 equals to 2.67, which of course is greater than our T, our critical value of 2.228. So we can reject and basically confirm that the slope is different from 0. Now I know it gave us the numbers in rounded form, but that's now a cool little thing that we may end up using. Alright. Question 27. Bradford Electric Illumination Company is studying the relationship between kilowatt hours used in a number of rooms in a private single-family residence. A random sample of 10 homes yielding the following. Number of rooms. We have 12, 9, 14, so forth, so on. Determine the standard error of estimate and the coefficient of determination. Interpret the coefficient of determination. Whew. Alright. So, basically we're doing this one right here, R squared, and the standard error of estimate right here. So let's go ahead and get them both in. So we need our data. So Excel. Go on to another sheet. Okay, put in our info. 12, 9, 9, 7. Ten, 8, 10, 10, 5, 4, 7, 7. So, I'm just going to do data analysis already. Then we're going to have to change the numbers. So, input our Y range, which again is our dependent. Put in our X. Make sure that all gets removed. Let's go ahead and clear them all out. There's that. There's that. Hit OK. Alright. So, here is our information right here. So this gives us all the regression that we need, which is cool. I'm enjoying doing these. So in case we need any information from here to make life a little bit easier for us. So here's our standard error from the data, significance, R squared, multiple regression, here's our standard error. So standard error is 0.913. There it is. So that's what they're asking for, standard error evaluation. And then, of course, it is asking for coefficient determination, which is r squared. Well, if I already did Excel, there's r squared. There's my coefficient of determination. So now let's have Excel work for us. Okay? So I know y'all know the formulas. I know y'all know how to do them. But now it's time to let the software to do it, because we're in crunch time. So the more fun stuff that we can learn to do that helps us, make it a little bit easier on us, the best we can. Oop, I went the wrong way. So that's answering question 27, just like that. Put in the information, and then go ahead and have the system solve itself now. Alright. It says determine the 0.95, I think, confidence interval in thousands of kilowatt hours for the mean of all 6 rooms. Determine the 0.9 interval in thousands of, so prediction and confidence intervals. So let's go check our Excel. So right now, our item does not give us the coefficient. These two intervals, it looks like. So we're going to have to break those down. Let's go find the formulas. So here they are. So we're going to have to find y hat, okay, minus t syx, and x minus x bar squared, and the sum of x minus x bar squared. Nice. So here it actually gives us the number that we need. So we need standard error. Okay. There's standard error. We need the t value. And we need y hat. And then the rest of the information. And we can pretty much get them done. So this is our intercept. Okay. So intercept, we do have our standard error right there. So we have those two numbers. Then we just need the t value. So it's a 0.95 prediction interval. And we know it's n minus 2. tables. I'm dealing with a 95. So we're looking at 2.306. So this is going to equal to our standard multiplied by 2.306 from our table. Yep. Okay. And then according, whoop. From our, current. Okay. So from our current slide, so we'll multiply by those, and we're going to have this fun formula that we're about to do. Okay, so multiply it by square root of 1 divided by 10 plus x, so x would be 6 room homes. Okay, so 6 minus x bar, so that'd be our mean. Divided by alright, I should just done it this way. So we're going to delete, enter right now, and we're going to come here, do x minus x bar, so we need to go x, go formulas, auto sum, take that, divide by 10, that's x bar. So this is going to equal x minus 9.1. Scroll down. Then do our square. Alright. Now find our sum. Yay! Okay. So, sheet 6, that has our formula. We now know to insert in our formula. Let's go to our formula. Okay. So, multiply now the square root of 1 divided by 10, multiply by power now of x, which is 6, minus from sheet 5, our x bar, comma, to 2, divided by the sum of our x minus x bar squared alright, then hit enter. Whew. So with that, all that fun stuff right there, we go to our Excel, okay, and then our y-intercept ends up being added together. That's our y hat. So, sorry about that. We need to find y hat. So, y hat equals to our intercept. Okay. Multiply by our slope. Okay, so our slope so back to Excel, which is right top. We have to add, not multiply. Man, I'm doing a lot of mistakes here. Plus, then multiply it by 6 equals to 5.33. Then we need to take plus and minus this. So this will equal this plus this for our high range. And equal to this minus this. Okay, that would be my actual confidence interval. Which looks like we have a little bit of rounding, but that's fine. All right, and then we would do the same for 1. For the prediction value, Except in our formula, copy and we put a 1. So it's 1 plus everything. And then again, take our coefficient, go equal this plus this, and equal this minus this. So there's our predictor interval and our confidence interval.